The morning of August 7th, 1944, 37,000 feet above the English Channel, German bomber pilot Hauptmann Werner Baake pushed his Junkers Ju-88 into thinner air, watching the altimeter needle climb past numbers that had once meant safety. For 3 years, altitude had been the Luftwaffe's refuge. Climb high enough, and Allied anti-aircraft fire became scattered mathematics, shells bursting uselessly thousands of feet below. At 7 miles up, where oxygen grew scarce and the cold bit through leather flight suits, German bomber crews had found sanctuary. But on this August morning, something had changed. The mathematics of survival no longer favoured altitude. Preparing and narrating this type of story took us long efforts and hard work. So if you are enjoying the story, please consider subscribing to our channel. Baake's bomb aimer reported the target, a supply convoy moving through the channel. Standard procedure called for descent to 20,000 feet for accurate bombing. But Baake hesitated. Intelligence reports had been troubling. Crews were disappearing, not shot down in the familiar chaos of fighter attacks, but simply erased from the sky by anti-aircraft fire that defied every calculation of probability. The rumours spoke of shells that tracked aircraft through clouds, that burst exactly where planes would be, not where they had been. Impossible precision at impossible altitudes. He decided to stay high, 37,000 feet, nearly 3,000 feet above the rated ceiling of American 90mm guns. The numbers promised safety, the cold comfort of physics and ballistic limitations. What Baake didn't know was that American gunners were no longer limited by physics. They had been freed from human reaction time, from trigonometric calculations scrawled on plotting boards, from the fundamental constraints that had governed anti-aircraft warfare since shells first reached toward the sky. Below him, and invisible on the Channel coast, an SCR-584 radar had already locked onto his aircraft. The system's microwave beam, operating at frequencies German warning receivers couldn't detect, tracked his every movement with accuracy measured in feet, not yards. Range, bearing, altitude, velocity, all flowing into an M9 director, an analog computer containing 160 vacuum tubes that recalculated firing solutions 30 times per second. The guns elevated. Not to where Baake's aircraft was, but to where it would be when 23-pound shells completed their 8-mile vertical journey. The mathematics were inhuman, calculated faster than any crew could think, accounting for variables that human gunners had never mastered. Wind speed at multiple altitudes, temperature gradients through the atmosphere, the drift imparted by the shell's rotation, the precise ballistic coefficient of each projectile, air density thinning with altitude, even the Earth's rotation. 4 90mm M2 guns, slaved to the director, moved in perfect synchronization. At 09:15 hours, they fired. The shells climbed through 7 miles of atmosphere in 42 seconds. Werner Baake never saw them coming. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The explosion occurred exactly where the M9 director predicted it would, not where Baake's aircraft had been when the guns fired, but where it arrived 8 miles later, flying into a calculated intersection of trajectory and time. The Junkers disintegrated. Fragments tumbled through thin air, following new ballistic paths that no human would ever calculate. Below, American gun crews were already tracking their next target. They wouldn't know for hours that they'd just achieved what German intelligence would spend months trying to comprehend. They had killed an aircraft flying 3,000 feet above the rated ceiling of their guns, at an altitude where thin air should have rendered the shells ineffective, where the time of flight should have made accurate prediction impossible. They had done it not through luck or overwhelming volume of fire, but through automation that eliminated every human limitation from the engagement cycle. The age of high-altitude sanctuary had ended. German crews simply didn't know it yet. The crisis for the Luftwaffe had been building since September 1940, when British scientists arrived in Washington carrying a device that would reshape the war. The Tizard mission, named for its leader Sir Henry Tizard, brought something unprecedented: the cavity magnetron. This seemingly simple device, a copper cylinder with precisely machined cavities, generated microwave radiation at power levels previously thought impossible. The cavity magnetron could produce 300 kilowatts of power at 10 centimeter wavelengths, a combination that made practical microwave radar feasible for the first time. The British, facing nightly German bombing raids, had developed the technology in desperation. But they lacked American industrial capacity to mass-produce the complex devices, and they lacked the scientific infrastructure to fully exploit its potential. The decision to share this breakthrough with American researchers represented one of the war's most significant technology transfers. What the British couldn't have anticipated was how completely American engineers would integrate this technology into automated weapon systems that would prove far more effective than anything envisioned in British laboratories. At MIT's Radiation Laboratory, established in December 1940, researchers immediately grasped the revolutionary implications. Microwave radar offered angular accuracy that meter wave systems could never achieve. The shorter wavelength allowed for narrower beams, which meant precision tracking, and precision tracking meant something that had eluded anti-aircraft forces since the First World War: the ability to predict aircraft position accurately enough to place shells precisely where aircraft would be, not approximately where they might be. The team at MIT, led by physicist Luis Alvarez and engineer Ivan Getting, began development of what would become the SCR-584 in early 1941. Their specifications were ambitious: a radar capable of detecting aircraft at 40 miles range, automatic tracking that required no human operator once a target was acquired, angular accuracy better than 1/10 of 1 degree, and most critically, the ability to track aircraft at any altitude within the gun's range, all the way up to the limits of where shells could physically reach. By April 1942, the prototype was ready for demonstration to Army Ordnance officials. It performed beyond expectations. Maximum range against large targets exceeded 64 kilometers, about 40 miles. Automatic tracking operated at half that range, providing continuous target data without human intervention. Angular accuracy reached 1/1000th of a degree, precision that made optical sights obsolete. The Army ordered 1,256 systems the next day. This wasn't incremental improvement over existing radar. It was a fundamental leap that would redefine what was possible in anti-aircraft warfare. The SCR-584 operated on frequencies between 2700 and 2900 MHz, wavelengths of 10 to 11 centimeters. German radar warning receivers, designed to detect British radars operating at 200 to 600 MHz, were completely blind to these emissions. Luftwaffe crews flew with electronic eyes that saw nothing, warning equipment that remained silent even as American radar tracked their every movement. This invisibility would prove decisive. Aircraft that crews believed were undetected were actually being tracked continuously, their positions updated dozens of times per second, fed into computers that calculated trajectories within human precision. The technical sophistication went far beyond frequency selection. The SCR-584 employed conical scanning for automatic tracking. The radar beam, offset slightly from the antenna's central axis, rotated at 4 revolutions per minute. When the beam swept across an aircraft, the return signal showed maximum strength. By continuously comparing signal strength as the beam rotated, the system could automatically adjust the antenna to keep the beam centered on the target. No human operator was required. Once a target was acquired and the operator switched to automatic tracking mode, the radar maintained lock regardless of evasive maneuvers. This automation eliminated reaction time from the tracking loop. Human operators, even highly trained ones, required fractions of a second to perceive target movement and adjust controls. Those fractions of a second accumulated into errors measured in hundreds of feet when tracking high-speed aircraft at long range. The SCR-584's automatic tracking responded instantly to target motion, maintaining accuracy measured in feet across ranges measured in miles. At extreme altitudes, where aircraft moved against empty sky with no visual reference points, this precision became decisive. The system's ability to track through clouds, darkness, and smoke added another dimension of lethality. Weather that grounded visual observation and optical tracking had no effect on microwave radar. German crews, who had relied on clouds for concealment, discovered that invisibility to human eyes meant nothing to electronic systems. Night missions, once relatively safe from anti-aircraft fire, became as dangerous as daylight attacks. The Luftwaffe's tactical playbook, built on exploiting weather and darkness, required fundamental revision. But that revision would come too late, if it came at all. Integration with the M9 gun director created the decisive weapon system. The director, developed by Bell Laboratories under the leadership of David Parkinson, was itself a marvel of analog computing. 160 vacuum tubes performed continuous trigonometric calculations, accounting for dozens of variables that human gun crews struggled to estimate. Shell velocity varying with powder temperature, ballistic coefficient changes with altitude as air density decreased, wind drift at multiple altitudes between gun and target, the time delay between firing and shell arrival, rate of change in target position, future target position based on current velocity and course. The M9 calculated firing solutions 30 times per second, updating predictions continuously as target data flowed from the SCR-584. Each calculation incorporated current atmospheric conditions, measured by meteorological instruments that fed data directly into the computer. Temperature, barometric pressure, wind speed and direction at ground level and estimated at altitude. Humidity affecting air density. Even the powder temperature of ammunition, measured in the magazines, factored into the ballistic equations. This was mathematics performed faster and more accurately than entire teams of human computers could achieve. The integration meant that once the SCR-584 locked onto an aircraft, the entire system operated with minimal human intervention. The radar tracked, the M9 calculated, the guns elevated and trained automatically, slaved to the director's output. Crews loaded shells and adjusted fuses according to settings computed by the M9. The shells fired. All human operators did was maintain the equipment and keep ammunition flowing. The decision cycle, from detection to firing solution to rounds downrange, occurred faster than human consciousness could follow. This speed mattered enormously at extreme altitudes. An aircraft at 40,000 feet, traveling at 300 miles per hour, covered 440 feet per second. The time of flight for a 90mm shell to reach that altitude approached 50 seconds. In those 50 seconds, the aircraft traveled more than 4 miles. Predicting where the aircraft would be required continuous calculation of its trajectory, accounting for any course or altitude changes during the shell's flight. Human crews couldn't perform such calculations with useful accuracy. The M9 could, and did, 30 times every second. Production of the integrated system demonstrated American industrial philosophy at its most effective. While German radar production remained essentially a craft process, with skilled technicians hand-building units that differed slightly from each other, American manufacturers applied automotive mass production techniques. Chrysler Corporation, assigned primary production responsibility for the SCR-584, transformed radar manufacturing from laboratory work to industrial process. By August 31, 1943, Chrysler had shipped 610 systems. Production accelerated as assembly line techniques refined. The original specification called for 1,470 systems, but the Signal Corps eventually contracted for 2098 units from Chrysler alone, including additional sets for the Marine Corps and coastal defense. General Electric and Westinghouse produced additional units. Total production exceeded 1,700 systems minimum, with some estimates reaching 2,500 units when all manufacturers were counted. This production rate exceeded Germany's entire wartime radar output across all types. While the Luftwaffe struggled to equip its fighters and bomber formations with basic radar warning equipment, American factories were mass-producing integrated weapons systems more sophisticated than anything in the German inventory. The production disparity reflected fundamental differences in industrial culture and military procurement. German emphasis on perfection and craft quality limited output. American emphasis on standardization and mass production enabled quantity that became its own form of quality. Cost reduction accompanied production scaling, Early SCR-584 units cost approximately $50,000 each. As production techniques matured and volumes increased, costs dropped below $10,000 per unit. This five-fold cost reduction while maintaining performance standards demonstrated manufacturing sophistication that Germany couldn't match under wartime conditions. The ability to produce high-technology weapons cheaply and in quantity would prove as decisive as the technology itself. Operational deployment began in early 1944, after bureaucratic delays that frustrated both developers and field commanders. The first combat use occurred at Anzio beachhead in Italy on February 24, 1944. Two complete systems were rushed forward and dug in, their trailers buried to rooftop level in the volcanic sand. German intelligence had learned to avoid strong points defended by traditional anti-aircraft batteries, but they had no warning that something fundamentally new awaited them at Anzio. That night, 12 German bombers entered the beachhead airspace. They flew in darkness, confident that night conditions would protect them from accurate anti-aircraft fire. The SCR-584 systems acquired the formation at maximum range, tracking steadily as the bombers approached. At optimal firing range, the M9 directors completed their calculations: 4 90mm guns per system, 8 guns total, elevated to computed angles and fired. 7 of the 12 bombers were destroyed, a 58% kill rate in complete darkness. The mathematics of this engagement would puzzle German intelligence for the remainder of the war. Surviving, German crews reported something unprecedented: flak bursts that tracked their every maneuver, explosions appearing exactly where aircraft would be seconds into the future, anti-aircraft fire that seemed to predict their decisions before they made them. Traditional anti-aircraft doctrine held that one kill required approximately 2,500 shells fired. At Anzio, the ratio approached 1 kill per few dozen shells. The improvement wasn't incremental. It represented a revolution in lethality that German intelligence couldn't explain because they couldn't conceive of the technology that made it possible. The Anzio engagement established a pattern that would repeat throughout the remaining months of war in Europe. German air attacks would target what appeared to be vulnerable positions. Formations would approach with confidence built on years of experience with traditional anti-aircraft defenses. Then, aircraft would start disappearing. Not scattered randomly by barrage fire, but systematically destroyed by shells that appeared with uncanny precision. Survivors would report impossible accuracy. Intelligence officers would file reports, and German High Command would dismiss the reports as exaggeration or excuse-making by demoralized crews. Air attacks on Anzio stopped for a week after that first night. German reconnaissance sent a single aircraft to test the defenses. It was destroyed. 10 additional SCR-584 systems were emplaced within the week. The Luftwaffe's ability to interfere with operations at Anzio effectively ended. What had been a crisis for Allied forces, German bombers attacking the confined beachhead with relative impunity, transformed overnight into a killing ground for any aircraft that approached within radar range. The German response to mounting losses followed predictable tactical evolution. If low altitude brought destruction, climb higher. If 20,000 feet proved dangerous, try 25,000. If 25,000 wasn't safe, push to 30,000. Altitude had always been the bomber's friend. Thin air reduced the effectiveness of anti-aircraft shells, their fragments traveling shorter distances in the reduced density. Longer time of flight made accurate prediction harder, and simple geometry meant that at extreme altitudes, even small errors in aiming resulted in shells passing hundreds of feet from their targets. German bomber crews had good reason to trust altitude. Throughout 1942 and 1943, high-altitude attacks had proven relatively safe. British anti-aircraft defences, while numerous, struggled with accuracy beyond 25,000 feet. American 90mm guns, while powerful, relied on predictors and plotting boards that couldn't compensate for the complexities of extreme altitude engagement. Crews who could coax their aircraft to 30,000 feet or higher operated with confidence that bordered on security. The Heinkel He 111, backbone of the Luftwaffe's bomber force, could reach altitudes above 22,000 feet when lightly loaded. The Junkers WWII, more versatile and capable, could operate effectively up to 30,000 feet. The Dornier d'Eau 217, though older, still served in high-altitude reconnaissance and bombing roles. German crews understood their aircraft's limitations, but they also understood anti-aircraft limitations, or thought they did. The mathematics they relied upon came from an era before automation, before radar-directed fire, before computers calculated trajectories faster than humans could think. By mid-1944, as Allied forces advanced across France and into the Low Countries, German bomber tactics had evolved into altitude obsession. Mission briefs emphasized ceiling performance. Crews stripped unnecessary equipment to reduce weight, trading armor and defensive armament for the ability to climb another 1,000 feet. Oxygen systems, always problematic, received meticulous maintenance because altitude was survival. Intelligence reports confirmed this thinking. Low-altitude missions suffered catastrophic losses. High-altitude missions, while less accurate in their bombing, brought crews home. What German intelligence failed to recognize was the correlation they weren't seeing. High-altitude missions were returning not because altitude provided safety, but because the SCR-584 systems weren't yet widely deployed. As production accelerated through spring and summer 1944, coverage expanded. Ports, supply depots, major road junctions. Anywhere the Allies needed protection from air attack, SCR-584 batteries appeared. And with them came a lethality curve that extended to altitudes German planners believed were safe. The 90mm M1 gun, developed in the late 1930s, had been designed with impressive performance specifications. Muzzle velocity exceeded 800 meters per second, about 2,600 feet per second. Shell weight was approximately 23 pounds, heavy enough to carry substantial explosive content and maintain velocity at altitude. Maximum elevation was 80 degrees, nearly vertical. These specifications weren't accidental. American ordnance planners had anticipated the need to engage high-altitude bombers that would appear in future wars. What made the specifications decisive was the maximum altitude figure. Official documentation listed ceiling at 43,500 feet, over 8 miles vertical range. This wasn't theoretical. Test firings had demonstrated that shells could physically reach this altitude with useful velocity remaining. The limitation wasn't the gun's capability, but the fire control systems available to direct it. Predicting where an aircraft would be at 8 miles altitude after 45 seconds of shell flight time exceeded human calculating ability. The gun could shoot that high. Crews simply couldn't aim it accurately at such extreme range. The M9 Director eliminated this limitation. Its vacuum tube computer performed ballistic calculations that accounted for every variable affecting shell trajectory at extreme altitude. Air density decreasing exponentially with altitude, requiring continuous recalculation of drag coefficients. Temperature gradients through the atmosphere, affecting air density and therefore shell velocity at each altitude increment. Wind shear, where wind direction and speed varied dramatically between ground level and upper atmosphere. The Coriolis effect, where Earth's rotation caused apparent deflection of shell trajectory over the long time of flight. These calculations happened 30 times per second, with each iteration incorporating the latest position data from the SCR-584. The result was firing solutions accurate enough to place shells within lethal burst radius of aircraft flying at altitudes German crews believed were sanctuary. But accuracy alone wasn't sufficient. The shells themselves required modification to remain effective at extreme altitude. At 40,000 feet, air density was approximately 1/5 of sea level pressure. This affected everything about shell performance. Fragments traveled shorter distances after burst, losing velocity rapidly in the thin atmosphere. Blast effect diminished as the reduced density meant less overpressure from explosive detonation. Contact phases became unreliable in the cold, where lubricants thickened and mechanisms sluggish. Traditional time fuses, requiring precise cutting to match predicted time of flight, introduced errors that accumulated over 40+ seconds of flight. The solution appeared in 1944, the proximity fuse. Developed in absolute secrecy, the proximity fuse was a miniature radar transmitter and receiver packaged inside an artillery shell. As the shell approached a target, reflections of its transmitted signal grew stronger. When signal strength exceeded a threshold, the fuse detonated the shell. This occurred automatically, without requiring precise time setting or direct hit. The proximity fuse transformed anti-aircraft gunnery from attempting to place shells exactly where aircraft were to placing them approximately near aircraft and letting electronics complete the engagement. At high altitude, where air density made traditional blast effects marginal, the proximity fuse proved decisive. Shells no longer needed to score direct hits or burst at exactly the right moment. They simply needed to pass within approximately 70 feet of an aircraft. The fuse would detect the target and detonate, sending fragments through thin air that might travel shorter distances but still possessed lethal velocity. The combination of SCR-584 tracking, M9 ballistic computation, and proximity-fused shells created a weapon system that made altitude irrelevant as a defensive measure. German crews first encountered this integrated system without understanding what they faced. The experience was psychologically devastating. Climbing to altitudes that had always meant safety, they watched shells burst alongside their aircraft with uncanny precision. Not barrage patterns fired in hope of lucky hits, but aimed shots that tracked through evasive maneuvers. Aircraft that jinked hard to evade predicted aim points discovered shells waiting at the end of their evasion, as if gunners had anticipated the maneuver. This wasn't anticipation, it was calculation. The M9 director continuously updated its prediction based on observed aircraft motion. When a pilot initiated evasive action, the SCR-584 detected the change in velocity vector within fractions of a second. New trajectory data fed into the M9, updated firing solutions transmitted to the guns. By the time the aircraft completed its maneuver, shells were already in flight toward the predicted endpoint. To German crews, this felt like fighting an omniscient enemy. Every decision they made seemed predicted, countered before it was completed. The psychological impact extended beyond individual engagements. Experienced bomber pilots had developed intuition about anti-aircraft fire. Years of combat taught recognition of barrage patterns, the skill of timing evasive maneuvers to avoid concentrated fire, the knowledge of safe altitudes for different target types. This accumulated wisdom became worthless against automated systems. Intuition failed. Experience provided no advantage. Skills honed over hundreds of missions offered no protection. The enemy wasn't more skilled. They were playing a different game entirely, one where human skill was irrelevant against machine calculation. Flight Lieutenant Hans-Joachim Hermann, who led German night fighter operations and later commanded bomber units, would write after the war about the psychological transition. We went from fighting skilled enemy gunners to fighting mathematics. Against skilled opponents, there was always the possibility that we were more skilled, better trained, luckier. Against mathematics, there was only the question of whether the enemy's calculations were correct, and they always were. This was not combat. It was execution by automation. The loss rates began to reflect this technological mismatch. In the first months of 1944, before widespread SCR-584 deployment, German bomber units operating over Allied-controlled territory suffered approximately 8 to 12% losses per sortie, painful but sustainable. By June, as coverage expanded around the Normandy invasion area, loss rates for missions approaching defended targets climbed to 15 to 20%. By August, missions within range of known SCR-584 batteries saw loss rates exceeding 25%. These were not sustainable numbers. Luftwaffe doctrine considered 15% losses the threshold where offensive operations became counterproductive. Beyond that point, loss of experienced crews degraded overall capability faster than training could replace it. At 25% losses, a bomber unit would effectively cease to exist as a combat-effective formation within 4 sorties. Yet German bomber crews continued to fly because orders demanded it, and because they clung to the hope that altitude would eventually provide safety. It wouldn't. It couldn't. The technology they faced had eliminated altitude as a variable that mattered. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The June 6th invasion of Normandy demonstrated the operational impact of comprehensive SCR-584 coverage. 39 systems were deployed to protect the invasion fleet and beachhead, carefully waterproofed for the amphibious assault. These units created an unprecedented defensive umbrella over history's largest invasion force. German intelligence had predicted the invasion, understood its approximate timing, and had bomber units positioned to attack. What they failed to predict was the complete inability of those bombers to penetrate the defensive network. Oberleutnant Joseph Pips Priller, one of only 2 Luftwaffe pilots to attack the invasion beaches on D-Day in his Focke-Wulf 190, survived to describe the experience. In post-war debriefings, he characterized the anti-aircraft fire as unlike anything encountered in 5 years of combat. Not barrage patterns intended to create zones of danger, but aimed fire that forced constant evasive maneuvering. Making accurate attacks became impossible when every second required violent maneuvers simply to survive. The larger German bomber formations, ordered to attack the invasion fleet that evening and in subsequent nights, encountered systematic destruction. Aircraft approaching at low altitude, attempting to use darkness and surprise, were tracked by radar that darkness didn't affect. Aircraft attempting high-altitude approaches, hoping to stay above effective anti-aircraft range, discovered that no altitude provided safety. The few that penetrated to release ordnance did so under such intense defensive fire that accuracy became impossible. Most never reached their targets at all. Within a week of the invasion, Luftwaffe High Command recognized that effective bomber operations against Allied positions in Normandy were impossible. Units were withdrawn beyond the range of Allied fighters and, more significantly, beyond the range where SCR-584 coverage was known to be comprehensive. This represented a fundamental admission of failure. The Luftwaffe, which had pioneered close air support and had terrorized Poland, France, and initially the Soviet Union with coordinated air-ground operations, could no longer operate effectively in the airspace over the primary land battle of the Western Front. Preparing and narrating this type of story took us long efforts and hard work, so if you are enjoying the story, please consider subscribing to our channel. The defense against Hitler's Von flying bombs provided the clearest statistical demonstration of the system's revolutionary effectiveness. The Von, essentially a primitive cruise missile, flew straight and level at constant altitude, making it theoretically an ideal target. But its speed, approximately 400 miles per hour, made it extremely difficult to hit with conventional fire control methods. Early attempts to intercept V-1s with traditional anti-aircraft methods achieved disappointing results. The weapons flew too fast for optical tracking, too low for effective fighter interception, and in straight lines that made barrage fire ineffective. 20 SCR-584 systems were assigned to England's Channel coast specifically to counter the Von threat, paired with 80 90mm guns using proximity-fused shells. These systems created a defensive belt through which every flying bomb had to pass. The results exceeded all expectations. In the first week, 17% of all flying bombs entering the gun belt were destroyed. This rose to 60% by August 23rd. By the last week of August, 74% were intercepted. On one extraordinary day, 82% were shot down. The ammunition efficiency improvement measured the technological revolution clearly. Traditional anti-aircraft methods required approximately 2,500 shells fired to achieve 1 kill. The SCR-584 integrated system reduced this to 1 kill per 100 shells fired, a 25-fold improvement in efficiency that reflected not better ammunition or more guns, but automation that eliminated human error from the engagement cycle. Every shell fired represented a calculated intersection of trajectory and target, not hopeful shooting at empty sky. German observers on the French coast reported seeing V-1s destroyed with short, precise bursts of 3 to 4 shells. This contradicted everything they understood about anti-aircraft warfare. Destroying a fast-moving target should require sustained fire, creating a zone of fragments through which the target flew. Instead, they watched as small numbers of shells burst alongside flying bombs with such precision that destruction came from single engagement. The observers recognized this as fundamentally different from any anti-aircraft fire they had witnessed. They simply couldn't explain the mechanism that made such precision possible. The German failure to identify the SCR-584 as the source of impossible anti-aircraft accuracy stemmed from catastrophic miscalculation at the highest scientific levels. In January 1943, German radar experts led by Professor Abraham Esau convinced the High Command that centimeter-wave radar was physically impossible. They argued, based on theoretical analysis, that insufficient energy would return to receivers at such frequencies to be useful for detection. This assessment led directly to Germany terminating all microwave radar research. Resources were redirected to improving meter-wave systems on the assumption that microwave technology was a dead end. When German forces captured a British H-2S radar in February 1943 and discovered it operated on centimeter waves, the revelation came too late. Germany had already fallen years behind in microwave technology development. The industrial capacity, scientific expertise, and time required to catch up simply didn't exist under wartime conditions. The decision to abandon microwave research ranks among the most consequential technical errors of the war. It guaranteed that German forces would face threats they couldn't detect, couldn't understand, and ultimately couldn't counter. German electronic warfare equipment, highly successful against British meter-wave radars early in the war, proved completely useless against the SCR-584. The Funkgerät 227 Flensburg detector searched for frequencies between 170 and 220 MHz. The Funkgerät 350 Naxos covered 2500 to 3750 MHz, theoretically overlapping the SCR-584's operating range. But Naxos was designed to detect search radars that swept beams across aircraft briefly. The SCR-584's conical scanning, which maintained continuous lock on single targets, produced emission patterns that German equipment didn't recognize as threatening. More fundamentally, even when German detectors registered emissions, crews didn't understand their significance. Radar warning receivers provided no indication of what type of system was tracking them or what threat it represented. A Naxos warning might indicate British H-2S, radar from a bomber, or it might indicate an SCR-584 preparing to guide shells into your aircraft. Without understanding the different threat profiles, crews couldn't take appropriate evasive action. They flew into radar-directed death traps, while their warning receivers remained silent or provided meaningless alerts they had learned to ignore. Luftwaffe crews flying into this technological nightmare developed a grim fatalism. Oberleutnant Heinrich Baer, who survived the war with 220 aerial victories, described in post-war interviews the transition from combat to calculated slaughter. Fighting enemy pilots was warfare as we understood it. Skill mattered, courage mattered, experience provided advantage. But flying against the radar-directed guns was simply mathematics. Our skill was irrelevant. Our courage changed nothing. We were numbers in an equation we couldn't see and couldn't influence. The only variable was whether the enemy's calculations were correct. They always were. This psychological dimension of automated warfare affected morale more severely than simple casualties. Luftwaffe pilots had accepted mortality as part of their warrior ethic. Death in aerial combat, while tragic, held meaning within their understanding of warfare. But death delivered by automation, killed by machines that calculated faster than humans could react, reduced pilots to objects in a ballistic equation. There was no honor in being destroyed by mathematics, no meaning in death that came from vacuum tubes and microwave emissions. By autumn 1944, the Luftwaffe's bomber force had been reduced to operational irrelevance over Western Europe. Units that had once numbered dozens of aircraft struggled to put handful into the air. Crews who survived multiple missions against SCR-584 defended targets often refused to fly again, not from cowardice, but from rational recognition that survival was impossible. The Luftwaffe's leadership could threaten courts-martial, but they couldn't reverse the technological inferiority that made missions suicidal. The introduction of jet aircraft provided no escape from the system's lethality. The Arado R-2-34 bomber, capable of speeds exceeding 450 miles per hour, and the Messerschmitt Me-262, adaptable to bomber role, promised performance that would render interception impossible. German planners believed that extreme speed would overwhelm Allied defences, allowing bombers to penetrate and escape before guns could engage. This hope ignored the fundamental capability of the SCR-584 integrated system. The radar could track targets at 600 miles per hour, faster than any operational aircraft of 1944. The M9 director calculated firing solutions for targets moving at speeds beyond human reaction time. Proximity fuses didn't care about target velocity. They detonated when targets approached, regardless of how fast those targets were moving. Jet speed, which made aircraft nearly invulnerable to fighter interception, meant nothing to automated systems designed to track and engage targets moving faster than any human could manually aim. Test engagements of SCR-584 systems against captured German jet aircraft, conducted after the war, demonstrated maintained effectiveness. The jet's speed compressed engagement time but didn't prevent accurate tracking or prediction. If anything, extreme speed made jet trajectories more predictable, as high-velocity aircraft couldn't maneuver as sharply without risking structural failure. The very speed that made them revolutionary as interceptors made them predictable targets for automated systems. German bomber crews never received the redemption that jet technology promised. The few jet bomber missions flown in the war's final months encountered the same impossible accuracy that had devastated conventional bomber operations. Aircraft that should have been untouchable due to speed found themselves tracked continuously, engaged by shells that appeared with precision unchanged from engagements against aircraft flying half as fast. The technology they hoped would restore balance simply extended the range of their irrelevance. The complete German intelligence failure regarding the SCR-584 represented more than missed observations or inadequate reconnaissance. It reflected systematic cognitive blindness, rooted in institutional assumptions about American technological capability. German military culture, particularly within the Luftwaffe's technical branches, maintained deeply held beliefs about German scientific superiority. These beliefs created filters through which contradictory evidence couldn't pass. Throughout 1944, Luftwaffe electronic warfare units operated with equipment designed for a war that no longer existed. Pilots reported impossible anti-aircraft accuracy with mounting desperation. After-action reports documented loss rates that defied explanation through conventional analysis. Surviving crews described phenomena that contradicted established understanding of ballistic limitations, yet German intelligence consistently attributed these reports to pilot error, exaggeration, or demoralization, rather than fundamental technological surprise. The pattern repeated across every theatre where Allied forces deployed the SCR-584. In Italy, bomber crews reported being tracked through clouds and destroyed in conditions where visual aiming should have been impossible. Intelligence attributed this to improved optical sights and better training. In France, high-altitude reconnaissance aircraft disappeared at altitudes previously considered safe. Intelligence concluded that Allied fighters had somehow achieved better high-altitude performance. Over the Channel, Von flying bombs were destroyed with efficiency that shouldn't have been possible. Intelligence suggested that more guns had been deployed, not that existing guns had become exponentially more effective. This failure of analysis stemmed from inability to conceive that American engineers had surpassed German capabilities in a critical military technology. The institutional mindset held that while Americans excelled at mass production, German science led in innovation and sophistication. Radar was a German strength, pioneered by German scientists, refined by German engineers. The possibility that Americans had developed radar fundamentally superior to anything in German inventory challenged core assumptions about technological hierarchy. When German forces finally captured an intact SCR-584 system near Saint-Vith in December 1944, during the Ardennes offensive, the revelation proved devastating. Dr. Hans Plendl, Germany's leading radar expert, led the technical examination. His report to the High Command, filed in early January 1945, represented an autopsy of German technological assumptions. The Americans had achieved automatic tracking with accuracy German scientists believed impossible. They operated on wavelengths German equipment couldn't detect or jam. Most critically, they mass-produced these systems with automotive efficiency, while German manufacturers struggled to build laboratory prototypes. Plendel's conclusion was brutally frank. Germany was not months behind in microwave radar development. They were years behind, with no possibility of catching up under wartime conditions. The industrial infrastructure required to manufacture cavity magnetrons at scale didn't exist in Germany and couldn't be created with resources and time available. Even if Germany could produce equivalent radar systems, they lacked the analog computing technology to replicate the M9 Director's capabilities. And even if equivalent systems could be developed, they couldn't be manufactured in quantities necessary to affect the war's outcome. The report represented strategic-level admission of technological defeat, but it came far too late to influence German tactical or operational planning. By January 1945, the Luftwaffe's bomber force existed primarily on paper. Units maintained organizational structure, but lacked aircraft, fuel, and experienced crews necessary for effective operations. The few missions still being flown occurred not because they served military purpose, but because operational planning hadn't yet accepted the complete obsolescence of German bomber operations over Allied-controlled territory. The technological helplessness experienced by Luftwaffe crews contributed directly to the January 1945 fighter pilots' revolt. Leading aces, including Adolf Galland, Johannes Steinhoff, and Günther Lützow, confronted Hermann Göring about the impossibility of their situation. These weren't defeatists or cowards. They were Germany's most decorated combat pilots, men who had collectively achieved over 500 aerial victories. Their willingness to confront Göring directly reflected recognition that traditional military virtues had become obsolete against automated weapons. Steinhoff, with 176 confirmed victories, delivered the assessment that Göring most needed to hear and was least willing to accept. "We are not fighting enemy pilots anymore. We are fighting mathematics calculated by machines. Individual skill has become irrelevant against automation. You blame us for lacking courage, but courage cannot defeat technology we don't possess. Our men are dying not because they lack skill or determination, but because they face weapons systems that make skill and determination irrelevant." Göring's response, relieving Galland of command and threatening courts-martial against others who had participated in the confrontation, demonstrated leadership's fundamental inability to accept technological reality. Rather than acknowledge that German forces faced adversaries with decisive technological advantages, Göring attributed mounting losses to insufficient fighting spirit and inadequate leadership. This denial persisted through the war's final months, as German units continued receiving orders to conduct operations that tactical reality had rendered impossible. The statistical evidence of the SCR-584's effectiveness accumulated throughout 1944 and into 1945. At Anzio, the first combat deployment demonstrated 58% kill rates in complete darkness against targets that traditional methods struggled to engage. Over the Normandy beaches, 39 systems created defensive coverage that effectively eliminated German bomber threat to the invasion. Against Von flying bombs, kill rates climbed from 17% to 82% as tactics refined and coverage expanded. The ammunition efficiency improvement measured the revolution most clearly. Traditional anti-aircraft doctrine assumed approximately 2,500 shells fired per kill achieved. This ratio reflected the fundamental limitations of human aiming against moving targets at variable altitudes and ranges. The SCR-584 integrated system reduced this to approximately 100 shells per kill, a 25-fold improvement that represented elimination of human error from the engagement cycle. Every shell fired by guns directed by the system represented calculated trajectory, intersecting predicted target position. Production statistics revealed industrial disparity that guaranteed German defeat regardless of tactical innovation. Chrysler Corporation alone manufactured 2,098 SCR-584 systems, General Electric and Westinghouse added additional units. Total American production exceeded 1,700 systems minimum, with some estimates reaching 2,500 when all manufacturers were counted. This single weapon systems production exceeded Germany's entire radar production across all types for the entire war. German radar production totaled approximately 4,000 units across all types, from simple warning receivers to sophisticated fire control sets. Most were meter-wave systems with limited capability. Microwave systems were essentially absent from German inventory after the decision to terminate centimeter wave research in early 1943. The production comparison understated the true disparity because it didn't account for capability differences. An SCR-584 system provided more combat effectiveness than multiple German radar sets combined. The manufacturing philosophy differences proved as decisive as the technology itself. The SCR-584 was designed for operation by drafted civilians with 6 weeks of training. Modular construction allowed field repair by soldiers with basic technical knowledge. Interchangeable parts meant that damaged components could be swapped quickly without specialized tools or expert technicians. Setup time from arrival at position to operational readiness was approximately 30 minutes. German radar systems required engineers and specialized technicians for operation and maintenance, needed hours for setup, and depended on craftsman-built components that couldn't be quickly replaced. These practical advantages multiplied the system's effectiveness beyond simple performance specifications. SCR-584 batteries could relocate rapidly, following advancing Allied forces and providing immediate air defense wherever deployed. German reconnaissance couldn't track their locations effectively because they moved too frequently. Luftwaffe mission planning couldn't route around defended areas because coverage areas shifted faster than intelligence could update. The operational flexibility stemming from rapid deployment and minimal crew requirements meant that relatively few systems created disproportionate defensive coverage. Beyond aircraft destroyed, the SCR-584's influence extended to missions never attempted and intelligence never gathered. German reconnaissance, essential for effective military operations, became impossible over Allied-controlled territory. Bombers couldn't reach targets to assess damage or identify new priorities. Photographic reconnaissance aircraft, even those flying at extreme altitudes, faced destruction rates that made missions suicidal. The intelligence vacuum this created degraded German operational planning throughout the campaign in Western Europe. General der Panzertruppe Hasso von Manteuffel, commanding 5th Panzer Army during the Battle of the Bulge, testified after the war about the operational blindness imposed by inability to conduct aerial reconnaissance. We attacked into the Ardennes, essentially blind. Our reconnaissance aircraft couldn't survive over Allied lines. We knew nothing of enemy reserves, movements, or dispositions beyond what ground reconnaissance could observe. The element of surprise, essential to our operational plan, was impossible to achieve when only one side could see the battlefield from above. This intelligence denial proved as decisive as direct destruction of aircraft. Even if German bombers had somehow achieved their targets and delivered ordnance accurately, the inability to conduct battle damage assessment meant that follow-up strikes couldn't be planned effectively. Commanders couldn't identify whether targets had been destroyed or merely damaged, couldn't determine which facilities had been hit and which remained operational. The fog of war, which aerial reconnaissance was supposed to penetrate, remained impenetrable for German forces, while Allied commanders enjoyed increasingly complete awareness of German positions and movements. For individual Luftwaffe aircrew, the SCR-584 represented something psychologically devastating beyond simple technological superiority. It embodied the reduction of human skill to irrelevance, the transformation of aerial combat from contest of warriors to execution by automation. Pilots who had trained for years, survived hundreds of missions, and earned Germany's highest decorations, found themselves helpless against machines that calculated trajectories faster than human thought. Hauptmann Heinz Wolfgang Schnaufer, the Luftwaffe's highest-scoring night fighter pilot with 121 confirmed victories, described in post-war interviews the psychological transition from hunter to prey. Fighting enemy bombers was warfare, we understood. We used skill, tactics, and courage to defeat adversaries who possessed the same qualities. But the radar-directed guns weren't adversaries. They were automated execution. There was no tactics against mathematics, no courage sufficient to overcome ballistic calculations performed by machines. We became objects in equations we couldn't influence. This dehumanization of combat affected morale more profoundly than casualties alone. Luftwaffe pilots had constructed identities around their warrior roles, accepting risk as inherent to their profession, but finding meaning in the contest of skills. Automated systems that eliminated the human element from combat destroyed this meaning structure. Death delivered by machines, calculating trajectories, eliminated honor from sacrifice, reduced experienced warriors to statistical entries in engagement reports, transformed aerial warfare into industrial process, where humans were simply targets to be processed. After Germany's surrender, Allied intelligence officers conducted extensive debriefings of captured Luftwaffe personnel, including demonstrations of the SCR-584 system and explanations of its capabilities. The reactions ranged from amazement to bitter recognition. Many expressed relief at finally understanding what they had faced. Others exhibited anger at German leadership's failure to recognize and respond to the technological threat. Some simply accepted the revelation as confirmation of what combat experience had already taught them. Dr. Wilhelm Rung, who had worked on German radar development throughout the war, admitted decades later the institutional blindness that had prevented recognition of Allied capabilities. We dismissed every report that contradicted our assumptions about American technical abilities. We created elaborate theories to explain impossible anti-aircraft accuracy rather than accept the simple truth that they possessed better technology. We attributed to pilot error what should have been recognized as enemy capability. This arrogance cost thousands of lives and contributed to our defeat. The broader military establishment's inability to recognize American technological superiority stemmed from cultural assumptions deeply embedded in German institutional thinking. The Wehrmacht, which had pioneered combined arms warfare and tactical innovation in the 1930s, couldn't conceive that American engineers had surpassed German military technology in critical areas. This cognitive blindness persisted even as evidence mounted throughout 1944. Each contradictory data point was explained away, attributed to factors that preserved existing assumptions rather than forcing their revision. Post-war analysis revealed that German intelligence had collected sufficient information to identify the SCR-584 threat by mid-1944 if that information had been properly analyzed. Pilot reports described tracking through clouds and precision fire at extreme altitudes. Electronic warfare units recorded microwave emissions they couldn't explain. Captured documents referenced new radar systems. The pieces existed to construct an accurate picture of Allied capabilities, but institutional assumptions prevented those pieces from being assembled into recognition of revolutionary threat. The failure extended beyond intelligence, analysis to strategic planning. Even if German leadership had recognized the SCR-584's capabilities in mid-1944, Germany lacked resources and time to develop effective countermeasures. Microwave jamming equipment would require years to design and manufacture. Tactics to avoid radar detection didn't exist for bombers that needed to reach specific targets. Standoff weapons that could be launched beyond radar range remained experimental. The technological gap was too large to bridge under wartime conditions. After the war, the SCR-584's principles became foundational to all subsequent air defense development. The radar was adapted for use in the AN, MPQ-12, and AN, MPM-38 systems. A modified version controlled the MGM-5 Corporal missile system, America's first tactical ballistic missile. The automatic tracking, computer-controlled prediction, and systems integration pioneered by the SCR-584 established templates that every modern surface-to-air missile system follows. The lesson that effective air defense requires removing human reaction time from the engagement cycle shaped military technology development throughout the Cold War and continues to influence current systems. Every modern air defense network, from Patriot to S-400 to Iron Dome, descends conceptually from innovations first demonstrated by the SCR-584. Automated tracking, computer-calculated intercept points, integration of detection, computation, and weapons into seamless systems. These capabilities, revolutionary in 1944, became minimum requirements for effective air defense by the 1950s. The Luftwaffe's destruction by these technologies provided clear demonstration that future aerial warfare would belong to whoever could automate the kill chain most effectively. The human cost of Germany's technological blindness cannot be precisely calculated. Records were destroyed, units dissolved, and survivors scattered across prisoner-of-war camps throughout Europe. But available evidence suggests that thousands of Luftwaffe aircrew died in engagements with SCR-584 directed weapons. These weren't deaths in equal combat between matched adversaries. They were systematic elimination of crews who flew into technological killing fields without understanding the nature of threat they faced. The tragedy extended beyond individual deaths to the waste of accumulated skill and experience. By late 1944, surviving Luftwaffe aircrew represented years of training and hundreds of combat missions. Their experience constituted irreplaceable institutional knowledge about tactics, aircraft capabilities, and operational procedures. Their destruction by automated weapons eliminated this expertise without the enemy needing equivalent skill. The veterans who might have trained new pilots, refined tactics, and preserved institutional memory were systematically killed by machines that didn't distinguish between novice and ace. General der Flieger Paul Deichmann, who commanded various Luftwaffe units throughout the war, provided post-war assessment that captured the strategic implications. We believed what we wanted to believe about our technological capabilities and our enemy's limitations. Every piece of contradictory evidence was explained away because it didn't fit our institutional assumptions. We couldn't accept that American engineers had achieved what our scientists declared impossible. By the time we faced reality, the Luftwaffe as an effective force had ceased to exist. The SCR-584 marked the end of aerial warfare as contest of individual skill and beginning of automated combat that continues today. For the Luftwaffe, this transition came as incomprehensible shock that their training, doctrine, and experience hadn't prepared them to face. They entered the war as warriors of the air, confident in their machines and their abilities. They ended it as victims of mathematical calculations performed by vacuum tubes and transmitted to guns that fired without human aiming. The system didn't just shoot down aircraft, it shot down the entire conception of aerial warfare that had existed since the First World War. The Luftwaffe thought war was about courage, skill, and superior machines. The Americans proved it was about technology, automation, and systems integration. German pilots were magnificent warriors, defeated not by better warriors, but by superior machines that eliminated the human element from combat. The Germans never knew that American radar devastated the Luftwaffe because acknowledging that reality required admitting fundamental inferiority in science, industry, and military innovation. That psychological barrier proved insurmountable until defeat made denial impossible. German leadership preferred to attribute mounting losses to pilot inadequacy, insufficient training, or demoralization, rather than accept that they faced technological threat they couldn't counter. This self-deception persisted through the final months of war, as German units continued receiving orders to conduct operations that tactical reality had rendered suicidal. For the aircrew who faced it, the SCR-584 was death calculated by machines, delivered with mathematical precision, immune to human courage or skill. They flew into electronic killing fields where their fate was computed before they arrived. Tracked by radar they couldn't detect, engaged by shells guided to calculated intercept points, destroyed by fragments from proximity-fused warheads that required no human judgment to detonate. The age of warrior pilots ended in the skies over Europe, killed by American radar that tracked invisibly, calculated instantly, and destroyed automatically. The legacy extends beyond the specific technology to the broader lesson about technological surprise in warfare. Convinced of their superiority, constrained by theoretical assumptions, unable to imagine adversary innovation, German leaders sent aircrew to face threat they didn't understand and couldn't counter. The failure wasn't primarily in intelligence gathering, but in intelligence interpretation. German observers reported American capabilities accurately. The reports were dismissed because they contradicted institutional beliefs about relative technological capabilities. This cognitive blindness proved more damaging than any security breach. If German intelligence had captured complete technical documentation of the SCR-584 in early 1944, institutional assumptions might still have prevented recognition of the threat's magnitude. The problem wasn't lack of information, but inability to accept that information challenged fundamental beliefs about German technological supremacy. This failure of institutional learning contributed as much to the Luftwaffe's destruction as the weapons themselves. The SCR-584 stands as one of World War II's most decisive weapons, not for the number of aircraft destroyed, but for what it represented: the triumph of systematic technological superiority over traditional military virtues, the automation of warfare to eliminate human limitations, the integration of detection, computation, and weapons into seamless systems that made individual skill irrelevant. German pilots never fully understood what they faced because their leadership couldn't accept its existence until defeat made denial impossible. Reports of impossible accuracy were dismissed as exaggeration. Evidence of automated tracking was ignored as theoretically impossible. Captured equipment that revealed revolutionary capabilities arrived too late to influence German response. By the time German scientists examined intact SCR-584 systems and understood the technology, the Luftwaffe had been reduced to operational irrelevance. The bomber force that had terrorized Europe in 1939 and 1940 couldn't effectively operate over Allied-controlled territory by late 1944. The Germans never knew until too late that they weren't fighting American gunners, but American mathematics embodied in radar systems that turned the sky into computed killing zone. Their courage became irrelevant factor in equations they couldn't see. Their skill couldn't overcome ballistic calculations performed 30 times per second. Their experience provided no advantage against automated systems that tracked through clouds, calculated through evasive maneuvers, and killed with proximity-fused shells that eliminated the need for direct hits. In that terrible revelation lay the birth of modern warfare, where victory belongs not to the brave but to the technologically superior, where human warriors become objects in automated processes, where the side that removes human limitations from the kill chain achieves decisive advantage regardless of enemy skill or determination. The Luftwaffe learned these lessons through the systematic destruction of its combat power, one aircraft at a time, each destroyed by shells guided to calculated intercept points by machines that never tired, never doubted, and never missed. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.